All right, hopefully that's recording. It says it is now. Okay, so let's dive in here then to perturbation methods and boundary layer theory. So we uh, talked through perturbation methods. We talked about asymptotic expansions and regular and singular perturbation problems. And we saw, for instance, in regular perturbation problems, you just substitute the asymptotic expansion in, and it sort of gets rid of the problematic term, but then it creates a lot of subproblems that you have to do. And in singular perturbation problems, it was even worse because it got rid of the problematic term, but it turns out the problematic term, is can't really get rid of. And so then we had to divide it into two problems: a problem where we had gotten rid of the term, and then another problem where it stuck around. And we had this sort of matching game where we did an inner region and an outer region, and we had to match them. And so now we're going to see how that applies to boundary layer theory. And so that's what we're going to talk about for probably the next week, I guess, and then we'll spend the rest of our in-class time reviewing for the uh, qualifying exam. So that's just as I'm thinking about that. Please send me any questions you have that you'd like to review for the qualifying exam. I'll probably send out a survey, just a quick Google form, so that you can sort of that'll prompt you to do that. But please do send me stuff because I don't know what you want to do, and we'll just sit and stare at each other if I don't hear anything from you this week. So I'll send out a survey on that shortly. Okay, so let's.
And Dr. Tree,
Oh,
can
please,
you
yeah.
probably just check your permission? I think Andrew is just trying to get in.
Oh, is he?
Yeah.
Yes. Let me pull up. There it is. Thanks, Chinyu. Okay, I see it now. Yeah, when I'm sharing the screen, I can't see that box easy. So sorry about that, Andrew. Okay, so here we go. Let us start then on two boundary layer theory. Okay, and um, so boundary layer theory is actually pretty important in transport. There are tons of problems that have this sort of fundamental feature of them. And so we're going to sort of back up and see why that is. So we're going to talk about external flows at high Reynolds number. Okay. And so the boundary layer problem uh, comes about in these kinds of in external flow. So an external flow is something where I have some object, okay, and pardon my drawing and on the computer, but I have some object and I now have fluid flow, usually forced convection that goes around the object. So the boundary layer problem. Okay, forced convection. Oops, convection around an object. Okay, so for example, this might be an airplane wing. Okay, it's pretty ugly airplane wing, but it could be an airplane wing. It could be a heated wire. It could be, something that you're depositing. If you're, doing combustion, they have this all the time where they stick in a probe, and that probe gets some deposit on that, and they're trying to use it to analyze what's happening in the system. Okay. And there are boundary layer problems for all of our transport cases. So there's momentum, there's heat and mass transfer involved. Okay. All kinds, right? But in all cases, as far as I understand, you first have to solve, if you remember forced convection problems, when we talked about forced convection problems, you first have to solve the fluid flow problem, and then you can add on top of that the heat transfer problem, or add on top of that the mass transfer problem. So the momentum transfer problem is a fundamental piece that you need before you can go on and do the other boundary layer problems. And so what we're going to focus on in our class for the rest of the time is we're going to focus on just the momentum. Okay, so it's the foundation and I'll put BLPs, boundary layer problems. Okay, so you're going to need that velocity field when you go to plug that into some, if you remember like the heat transfer equation, there's the big dV/dt, right? Big dV/dt, right? Or excuse me, like CA dt. I guess that's mass transfer, right? Which has the partial CA dt plus V dot, grad CA, right? And that we're going to need to get. So if we're going to do a mass transfer problem, we need the velocity first, right? To be able to do that. All right, I need a new page. All right, so let's set up an example then. So let's just do a quick example to think about the length scales involved. So I've got some object. It has length L. So I'm going to have flow around it like this. Ooh. I'm going to stick to laminar flow here. Okay. And there's going to be some velocity far away that I'll call V infinity. And then there's some of density and viscosity of the fluid. And we're going to assume that these are constants. Okay, so we're going to assume incompressible flow. So like I said, V infinity was the velocity far away. Okay, it could be a vector. And then L is the characteristic size of the object. Okay, so if it's a circle, that might be the radius or the diameter, right? We can pick. And so if we recall our equations, the governing equations for momentum balance are as follows. It's the Navier-Stokes equation. So we have rho dv dt plus v dot grad v. That's equal to minus grad p plus mu grad squared v. Okay, and then we also have the continuity equation with that momentum equation, del dot v equals 0. And for this external flow problem, we're going to have the following boundary conditions. We're going to have v equals 0 on the surface. Okay, that's the no slip condition, right? And the other one we're going to have is that v is equal to v infinity at, I'm going to call it r goes to infinity. So far away from the object, okay? And I'm going to also define v infinity without vector as the magnitude of v underscore infinity. Just if I ever do that and leave that off, just know that that's the magnitude there. Okay, so any questions about the sort of first setup of the problem? Okay, so that looks pretty straightforward then. So the first thing we're going to do, and maybe by now you're coming to expect this, we're going to non-dimensionalize this guy. How many of you expected me to say that? Yeah, Brian owns it. Brian owns it, okay? So the first thing we're going to do is non-dimensionalize it. So if I'm going to define x's, I'm going to have x over L. I'll have gradients, which will also use L. So there'll be L gradient. Velocities, I'll scale by V infinity. Let's see, what else do I have? I have a pressure. Remember, there's two pressure scales. There's an inertial pressure scale and a viscous pressure scale. We're going to use the inertial pressure scale, which is rho V infinity squared. And then we have time, and time we're going to scale by the convective time scale, which is Well, I wrote it down in my notes wrong, but I think it's L over V infinity, if I'm not mistaken, right? Because I have length per time, and so is that right, or is it upside down? I think is that upside down?
Time should be on the denominator.
So this should be like, should it be like this? V infinity over L?
Yeah. Yep.
Yeah, thank you. Okay. All right, so we've actually done this before. Do you remember when we non-dimensionalized the Navier-Stokes equation way back when, and we talked about Euler's equation and Stokes equation? So we're going to get Euler's equation here. So we'll do it really quickly because we've done this before. But we just take these definitions, right, and plug them back into here. The continuity equation is going to be boring. We're just going to get a V infinity and an L that cancel out 0. So the continuity equation, we end up with del tilde dot V tilde is equal to 0. So that one's pretty straightforward. The Navier, the momentum equation is a little bit more work. So let's do that. We're going to have rho, and then if you look here, I've got dv dt, so I'm going to have a V infinity in the numerator from V over here, and then I'm going to have t in the bottom, so I should have a V infinity and then an L. Is that right? No, that's wrong. I have to have it upside down because I multiply that over, so I have that backwards. So I put an L down here and a V infinity squared, and I'm going to get dv tilde dt tilde plus, now I have V dot grad V. So I have a row from the parentheses over here. I've got a V infinity and then a dot. The grad, I'm going to get a 1 over L. And the V, I have another V infinity, so that'll be V infinity squared. That makes sense. Those should have the same units. So now I'll have a V tilde dot grad V tilde, grad tilde. Okay, and that's the left-hand side. And then on the right-hand side, I'm going to get a minus grad P. So I have a minus, grad gives me a 1 over L, and a pressure gives me a rho V infinity squared. And then I have a grad P tilde. And then the last one is mu grad squared V. So grad squared gives me an L squared in the denominator. And then I have another V, so that should give me a V infinity. And that'll, let's see, grad tilde squared V tilde. Okay, so did I lose anybody on that? Okay, so now I've got rho V squared over L, rho V squared over L, rho V squared over L, and then not rho V squared over L. So let me multiply by the inverse of this. That'll cancel that, that, and I should just get something in front of that term. And let's get a new page here and see what happens there. So I end up with dv tilde dt tilde plus v tilde dot grad v tilde is equal to minus grad p tilde plus, and then I have L over rho V infinity squared multiplied by mu V infinity divided by L squared grad squared V tilde. Okay, and we look at this guy and we get an L that cancels there and a V infinity that cancels there. And I have rho V infinity L over mu. So that's 1 over the Reynolds number, right? Rho V D over mu, rho V L over mu. So that's the Reynolds number with L. So I have my final thing. And just to save myself a little space, I'm going to write the left-hand side as the material derivative to save my hand a little bit. dv dt is equal to minus grad P plus 1 over the Reynolds number grad squared V. Okay, so that's the dimensional analysis for that guy. So that's our final thing. We also have del dot v, which we wrote up earlier, equals 0. And then we have our boundary conditions, which are v tilde is equal to 0 at the surface. And now we have v tilde is equal to, and if we substitute in v infinity, we had a v infinity over here. So v infinity divided by v infinity gives us a 1. And so now we have a 1 far away. Okay, so now we have our dimensionless set of equations that we can solve. Okay, any questions about how I got to these dimensionless equations? That should be pretty straightforward, right? So now for a boundary layer problem, we assume, okay, or we're interested in the case of the Reynolds number being much bigger than 1, right? Fast flow, okay? And in that case, what do we expect to have happen? Well, if Reynolds number is much bigger than 1, then we can say 1 over the Reynolds number is equal to some small value epsilon, which is much less than 1. Okay, and so now we can think about writing a perturbation expansion, right, where I write down v, right, is, epsilon to the 0 v0 plus epsilon to the 1 v1 plus etc. Right, so I'm writing down now some asymptotic expansion in terms of 1 over the Reynolds number. Okay, and so at order 0, at order epsilon to the 0, recall that that means that the term with the epsilon in it is going to go away, right? That term goes away. So at order 0, I get back dv dt equals minus grad p. And I get del dot v equals 0. Okay, so I lose this term over here, the term with the viscosity in it. Okay, and so remember that this one is Euler's equation, if you recall. Okay, which we said was valid for high Reynolds number. Okay, so let's think about this in the context of our perturbation problems. So is this a regular perturbation problem or a singular perturbation problem? Don't all jump at once here.
It's singular.
It's singular, that's right. So can you explain to us why it's singular, Mark?
The second derivative went away.
Yeah, the second derivative went away. It's actually a lot like our problem that we did before, right? We had a convection part and a diffusion part, and here our diffusion part went away, right? So think about what that's going to mean on our, surface, right? We're assuming, right, that the Reynolds number is really high, right? Reynolds number is really fast out here, right? But now we've lost any chance of diffusion, and somewhere here, right, the velocity has to go to 0 at the surface. So we've done the same thing that we did in that singular problem we did last time. Somehow there have to be two regions, right? There has to be a region out here where we can neglect the viscous forces, okay? But then there has to be some inner region in here where those viscous forces aren't 0 and they're important. And so that diffusion term is going to come into play. Does that make sense? So I see some staring, and I just sort of, like, we could go through the math on a specific example, and we are going to in a minute, but we could go through the math with a kind of complicated and show that, for instance, if we assume this Euler equation, we're going to end up with not being able to satisfy the boundary condition on the inner surface. And as a matter of fact, this is a, I was thinking this is like some of these boundary layer problems, these could be a good problem to do for your project. You could pick a boundary layer problem like a wire or something where you have to solve both momentum and the thermal boundary layers, and you could sort of work this out. And in cylindrical geometry, you can see that this doesn't happen. And we talked about this if you took my undergrad fluids class, and hopefully you talked about it somewhere in fluids, about what's called D'Alembert's paradox. And so it turns out, and we'll talk about this that in a second, that when you solve for this outer region, okay, and then you try and calculate the drag force is 0. And that's because there's no viscous forces acting anywhere. And it seems like you shouldn't get a drag of 0, but you do. And that was really confusing to people for a long time. I think D'Alembert mostly was confused, right? He brought the problem up, and then it didn't get resolved. It sort of got resolved. People sort of figured out boundary layers without figuring out the asymptotic expansions. And then it really got figured out when people figured out asymptotic expansions in the 20th century. So the boundary layer problem is actually a non-trivial problem that took a long time to try and figure this out. Okay, so remember, what did we do for singular perturbation problems to solve this issue? So if we know that what's going to happen is there's going to be this inner region here, okay, and then there's going to be an outer region out here. Maybe I'll back up and ask a different question. Where is Euler's equation going to apply? Is it going to apply in the inner region or the outer region?
The outer region.
It's going to apply in the outer region. That's right. So this is where Euler's equation is. Okay, so we're going to need to then solve a different problem for the inner region. So do you remember, how did we go about doing that? What did we do when we wanted to do something for the inner region? I don't know, that was the part you've got lost. Too many smiles to, okay, so in the inner region, we had to rescale. So if you recall, okay, we had before, a variable, and we did the same thing here, where we used the length scale of the entire object, right? So we said that was our characteristic size of the object, was that big length scale. And that comes out in our Reynolds number here. But remember, when we did this problem with the singular perturbation before, we had to pick a little length scale. And we didn't know what the little length scale was, but we had to guess at it, right? So we had to guess, it could be this length scale, it could be this length scale, it could be this length scale, okay? And when we tried a bunch of different length scales, one of them worked to make it so that our problem wasn't singular anymore, okay? And that special length scale is the size of the boundary layer. We might not know what it is, but that's what the size is. So that's the same thing that we need to do here, okay, is we need to rescale somehow. So we need to rescale. Using the size of the boundary layer. Delta. I guess it doesn't have an underline, delta, but we don't know what the size is yet. Okay, maybe you remember from fluids. Who remembers from fluids what the size of the boundary layer is? Does anybody remember? Okay, if we don't finish it today, you'll be in suspense. Looks like we may or may not quite get all the way there, but you can go back and look at your fluids notes or your fluids book and see if we end up at the same place that we did in fluids, okay? I did want to say one quick aside real quick. So this is kind of back to Euler's equation, which is, how do we solve Euler's equation? Okay, and it turns out there's a shortcut. So Euler's equation is kind of hard. If you look at it, you've got the same problem you have in all of momentum problems. You have the continuity equation and Euler's equation here, and there's a problem in that you have to try and get the pressure, and it's a pain. Okay, and so there's a shortcut that pretty much everybody uses all the time, and it turns out that it has to do with what's called inviscid flow. And I always thought this was really counterintuitive, and it took me until I taught fluids to really understand why people care about this. So it turns out that if you're in this outer region out here, there's no viscosity. And it turns out that viscosity or viscous, I'm going to say this differently, viscous forces, they generate what's called vorticity. Okay, and vorticity, if you remember from your fluid mechanics class, is defined as the curl of the velocity. If I can write a curl, okay? So you need a viscous forces to generate vorticity. So if you're in this outer region out here and you're inviscid, and if the flow has no vorticity here, then the flow over here also has no vorticity, okay? And that's a theorem that's called Kelvin's theorem. Okay, so if you have, laminar flow out here, it'll stay so long as you're in this outer region. You can have no vorticity then. Okay, so inviscid flow is when the vorticity, which is again the curl of the velocity, is equal to 0. Okay, so that's inviscid flow, and Kelvin's theorem says that if I start inviscid in that outer region, then I stay inviscid in the outer region. So you can use this as a way to derive a different set of equations. And so you never actually solve Euler's equations directly. It's easier to solve a different set of equations. So this fact right here implies the following. It implies that the velocity is equal to a gradient of some other function, which is called the velocity potential. Okay, so I wrote the arrow the wrong way. This implies this, okay, because of math, right? There's this thing called the Helmholtz decomposition theorem that you can go look up, because I forgot to write it down in my notes, and I don't want to write it down wrong. But basically, the Helmholtz decomposition theorem says that you can divide any vector field into a part with a curl and a part with potential, like this. That this is a valid way to decompose any velocity field. And so because of this, if you know that the curl is 0, then you can say that the velocity has some velocity potential, okay? So that implies this. And then you take that piece and you add on to it the fact that you know that del dot V equals 0. And that implies that del dot grad phi equals 0, or in other words, grad squared phi is equal to 0. And this is what people solve instead, okay? This is called the Laplace equation, okay? And it incorporates the continuity equation. It's linear, okay, second order PDE. It's a super common PDE. You see this in heat transfer, for example, if you have a time independent heat transfer problem. And so people will solve the Laplace equation, then you use phi to get back the velocities, and then you can use the velocities to get the pressures if you need the pressures up here from Euler's equation. Okay, so you can use that to get the pressures. Okay, so long as you're in inviscid flow, that works. And that's almost always the case, because if you're saying an airplane, you might think, well, how is that inviscid? I've got these big wakes and whatever, but it turns out the wakes are in the inner region. And so you only care about the outer region, and you can solve for this Laplace equation on, using the shape of the wing. And we'll see in a second how that's going to couple to our boundary layer problem. Okay, so that was just a quick aside about how to solve that outer problem. Are there any questions about that? That was kind of a winding explanation, and I skipped all of the dirty math, but any questions about the Laplace equation or the velocity potential? All right. I'm not missing anything in the chat, am I? I haven't checked the chat in a long time. Okay. All right. So let's, so where were we? We were up here and we said, well, we need to rescale to talk about the inner region. And that actually leads us to a whole separate subsection here, which are called the boundary layer equations. So B are boundary layer equations. Okay, boundary layer equations. Okay, and these are rescaled momentum equations. Okay, so what we're going to say here then is, so now we're going to look at the inner problem. Okay, and just like I said before, just to remind us, we need a new length scale. Which is delta, which is the size of the boundary layer. Okay, or in other words, the size of the inner region, right? There's not two R's in inner the last time I checked. Inner region. Okay, looks like I need a new page. Okay, so, and to be really specific so that we can have a really specific example here, we're going to pick a geometry. So let's look at a flat plate. So a flat plate will turn out to be the easiest boundary layer problem that I know how to solve. Maybe the only one that, that's not true. I know how to solve the other ones. I don't know if I've ever solved them all the way out, but the boundary layer problem, or the flat plate one, we can do. Okay, so remember, we're going to have something like this. Delta, it's going to be the size of the inner region. L is going to be the length of our plate. Okay, I'm going to define X and Y coordinates as follows. X over here, Y this direction. Okay, note that the outer solution is trivial for a flat plate. It's just V is equal to U dx. Okay, so I'm calling V infinity U here because I'm also going to have a V that I'm going to want to rescale. So that'll help make my life a little easier to call that U instead of making sub-infinities and having lots of V's around. The other thing is, it turns out, this is kind of interesting. Another reason why the flat plate is a good problem to look at. It turns out that if delta is really small relative to L, then the curvature of this surface doesn't matter very much. So if you think about like a cylinder, right? If I zoom in far enough, it looks like a flat piece when I zoom in enough, right? And so it turns out that you can show that if I take the Navier-Stokes equations in cylindrical coordinates and look at the inner region, I end up getting the exact same boundary layer equations as I'm going to get for a flat plate. And so it turns out that this inner problem is very similar regardless of the geometry. Okay, so inner problem for a flat plate is almost the same for all geometries. And it's not exactly the same, but there's only one term that's different. And I'll point out which one it is, okay? It's almost the same for all geometries because curvature doesn't matter. Okay, and I'm not gonna go and do the detailed derivation for this out, but if you'd like to see it, there is a transport book that has it. It's by Gary Leal. That's called Advanced Transport Phenomena. And this is in section 10F in that book. Okay, Gary Leal was at UC Santa Barbara, kind of a famous transport dude. And I think they're the only university that I know of that use his transport book. And I talked to the graduate students there once about it, and they're like, it's terrible. It's way over our heads. We get really grumpy, but they use it here. I think most everybody else uses Bill Dean's book. And some people use Burster and Lightfoot like we do. Okay, so let's do the rescaling. Let's do that. Okay, this is dimensional analysis again. Okay, but this time we're going to pick different scales. So we're going to start with the continuity equation. So let's do, I'll write the continuity equation right here, continuity. Let me pause real quick before I dive in the math. Are there any questions about the idea of the flat plate or about this idea about rescaling really quick?
I have a quick question.
Yeah.
Delta is a function of L, is that correct?
Yeah, well, technically not of L, so it'll be a function of X.
Oh, sorry, of X, yeah.
Delta is going to end up being a function of X. L, right, is just the length of our plate overall.
Okay, it'll probably end up clearing up. I'm just trying to imagine non-dimensionalizing something when that term can be variable and not a constant, but I'm sure it'll smooth itself out.
Yeah, we'll see how that comes out. Yep, that'll pop up in the derivation. So yeah, please.
What is the E in the V equals U EX?
Oh, that's the unit vector for the X direction.
Oh, okay.
Right. So yeah, good question. I didn't say that. So EX would be like that direction. EY would be the upper direction. So all I'm saying there is the outer solution for a flat plate's really easy, right? It's just whatever the velocity was coming in, it's just the same on the top. So that makes the perturbation problem a lot easier if you just have a simple outer solution, right?
Mm-hmm.
Okay, so for the continuity equation, let's see if we can finish this one before the end of class. So we're going to need to define some different scales. So maybe I'm going to actually move this down. That's maybe cheating. You can't do that on your paper. Go back to my pen. Okay, so I want to define some scales. So we have X. We're going to keep X as X over L, but we're going to define Y now as a different scale, right? Because X has this length scale here, L, but Y is going to have this scale, delta. Okay, so we're going to write Y is Y over delta. Then Vx, we have a length scale for Vx, which should be Vx over U, where U is the scale here. Sorry, I keep scrolling down. It's hard for me to write at the bottom of my screen. But I don't know what the scale for Vy is going to be. So Vy, I'm also going to leave unknown. I'm going to call that big V. Okay, so I have a big U and a big V. And then I'm going to keep my pressure scale the same. Pressure, I forgot to put tildes on these V's. Pressure is still going to be P over rho U squared, where U is that outer thing. Okay, so now I can jump to the continuity equation. Sometimes I wish I could do that in my notes for real. Okay, here we go. So in continuity, I have dvx dx plus dvy dy is equal to 0. And for a flat plate, I can assume 2D. So I didn't really note that, but I have 2D for a flat plate. Okay, because the depth doesn't really matter. So now let me plug in these things here. So I've got dvx dx, so v has a u, so I get u, and then I get a dvx tilde in the top. And then x in the bottom, I'm going to get an L. So u over L dvx dx tilde. And then vy should look similar, but I have a v and a delta that come from those guys. So dvy dy tilde is equal to 0. Okay? And so I can divide by this guy and combine over here. And I'm going to get dvx dx plus LV divided by delta U dvy dy is equal to 0. Okay? And what I'm going to say is that I'm going to use this thing here to find V. So I'm going to say LV over delta U is equal to 1. I'm going to use this to find V. Okay, and why can I do that? I can do that because if we go back to the pi theorem, we'll figure out that I don't have any other degrees of freedom other than the Reynolds number. So I can't have any other dimensionless groups. And so this one has to be equal to 1, right? Or I could make this one not 1 and something else would happen with the Reynolds number. But it's a lot more simple to keep the Reynolds number and get rid of this one. Okay, so I'm going to use this instead and find V. So if I rearrange that, I'm going to get V is equal to delta U divided by L. Okay, so that tells me that, if delta is a small number, right, this is basically delta over L times U. So whatever the velocity is on the top, I'm going to get a velocity in the y direction that's a lot smaller. That makes sense. I wouldn't expect a lot of velocity there. But what's going to happen is as I'm near the plate and the velocity slows down there, some velocity is going to have to go up, right? And that's because of continuity, right? The mass balance says that. Okay, so we'll pick up our derivation of the boundary layer equations next time. We'll just stop here, but I'll pause for 30 seconds and see if there's any question. Probably not full 30 seconds, 10 seconds. Okay, looks like everybody's ready to go. All right, so we will pick up from there. Please email me if you have any questions about your project. I'm happy to chat, and thanks for paying attention, everybody.
Thank you.
Yeah, see you guys.
Dr. Tree,
What's up?
I'm sorry, I got on too late for you to see me get on, but could you just give me a quick rundown of what you went over in the first couple minutes of class?
Yeah, so I basically just asked if there were questions about the project. I believe one question was about if someone wanted to do a problem that was a part D, if they needed to have a paper. And I said, sort of as I was going through the project, I came to the conclusion that I cared a lot more about the problem than I care about a paper per se. And so what I'm really looking for is a good sort of transport problem that goes beyond just a homework problem, right? So, and so I can talk a little bit more about that if there's a question there. The other question was, I think Tyler asked, where were their example papers? And they are on Learning Suite. So on Learning Suite, there's a new content tab that says project, and there's the PDF again for that. And then there's a zip folder that has about 8 papers in it. And another thing I said about that is there are some papers that have like a single problem. There are some papers that have sort of what I would consider multiple projects in them. So one of them I gave was a review paper that talked about electrophoresis and diffusiophoresis and a bunch of other stuff. And I said that, there you would want to say just pick one, right? And look through that one. And so I'm more than just a paper. I'm interested in sort of using a paper and maybe a book to sort of dive into a problem that's in your area or whatever you're interested in, and get into that. Does that make sense?
Yeah, totally. Thank you. That's awesome.
All right. Any other questions about the project from you?
No, I think that's good. I was thinking about looking in, I know you mentioned in the last class that we could look at like book problems that we didn't really like finish and see how that connects to some paper that they reference, or book problems that we didn't really ever do. I'm pretty sure I saw some about like nuclear fuel rods, so I was probably going to go look into that.
Yeah, I think that'd be great. That would totally be a good problem. Yeah, what I'm really hoping is that you can dive into that problem enough where you can use some of the methods or some ones that we didn't talk about, but some of these methods to solve some of these problems that maybe are of something that kind of catches your interest like that. So I think that'd be great.
Awesome. Okay, cool. Thanks, Dr. Tree.
Okay. Yep.
See ya.
See ya.